Good morning.
Good morning, ma'am.
Good morning,
Good
ma'am.
morning, ma'am.
Good morning, ma'am.
So far, we have discussed your Rankine cycle, that is theoretical Rankine cycle, and also we have discussed the practical Rankine cycle. So in that case, we were including the um, efficiency of turbine and efficiency of your compressor. So there we are considering both the actual work done by the turbine and work input in case of your pump or compressor. So then we were finding out the efficiency in terms of the work output, that is your actual work and theoretical work in case of both the compressor and in case of your turbine. Okay, so we have some idea about that Carnot cycle also. In your last semester, I have explained you that we can also use the Carnot cycle, which is the basic cycle for the all the heat engine. So in that case, the heat addition. So generally in that case, we were doing the heat addition at the constant temperature, then up to the saturated vapor line, that vapor will form as the saturated vapor. Then again we were doing the reversible adiabatic expansion process. So this process is similar to the Rankine cycle, right? And then again also there is the constant temperature heat rejection process. This is the heat addition and heat rejection process. Then again up to this we were doing the heat rejection. So condenser heat is rejected up to this. Then again there will be the reversible adiabatic uh, compression process. So this was the compression process. This was the expansion process. So this is the working or thermodynamic cycle, um, while we are considering the Carnot cycle. So this will be your steam power plant process. So this I have done for in case of the TS block. So if you will observe in this case, the reversible adiabatic expansion and reversible adiabatic compression process, these two are similar with that of Rankine cycle. So if you have remembered that Rankine cycle TS plot, then it will look like this, right? So there is the heat addition process is at the constant pressure. So this one I have taken up to the saturated vapor. You can take up to the superheated also if it is the superheated steam. So to comparing these two, I have taken the saturated state of the vapor. Okay, which is entering to the turbine. So in case of the Rankine cycle, if you have remembered, this is the 4, 3, 1, 2, right? So 4 to 1, there will be the heat addition. So that is done at the constant pressure. So heat rejection, which is at the constant pressure. So both the process, that is the 1, 2, and 3 to 4, both are reversible adiabatic. So these two, this is the expansion process in case of the turbine 1 to 2, and 3 to 4 is the compression process. This is also reversible adiabatic. So these two processes are same with that of the Carnot cycle. The only difference is the heat addition and heat rejection. So here in this case, if you will observe, the compression will handle the both the phase of the substance. That means here it is the liquid and vapor mixture. So within this vapor dome, there will be the liquid vapor mixture. So it is quite difficult to handle the two phase of the substance to compress right? So in this case, that is one drawback. Another thing is that at the constant temperature, we cannot add more heat. At the all of you know that the whatever heat is added, that in case of the constant temperature, that will be less than this heat addition at the constant pressure. So that is also one drawback to use these Carnot cycles. Whereas this is the basic cycle for the all the heat engines. So these two are both are ideal theoretical cycle. So here I have taken all the processor reversible process. Um, mm, in case of the Carnot cycle, here the temperature, the operating temperature is maximum as compared to this Rankine cycle. So as for that reason, so heat addition is more in case if we are taking the maximum temperature. In that case, your efficiency will be more as compared to your Rankine cycle. Okay. So in case of the Rankine cycle, as I have told you, all the processes are reversible, and at the constant pressure, we are adding the heat. And in case of the Carnot cycle, all the processes are reversible. Heat addition is the isothermal process. So Q2, we can say heat rejection is same for both the case. So there, if Q2 is less, then the efficiency of the both the cycle will depend upon the heat addition. That is your Q1. Okay. So for the in that case, um, the heat addition will be more in case of the Carnot cycle. So in Carnot cycle, pump has to do more work to handle this um, liquid vapor mixture. This is one drawback of this Carnot cycle. Okay, so it is very difficult to control the quality at this point. So um, that's why the compression in case of the Rankine cycle, we are performing up to the saturated liquid state. Okay, so this is the two difference. So now I'm going to discuss the mean temperature of heat addition. What is that one? So, in case of the Rankine cycle, the efficiency of the Rankine cycle will depend upon the mean temperature. So, mean temperature means the temperature at which we can get the maximum cycle efficiency. Okay. So, the Rankine cycle efficiency is the function of your mean temperature. That is your TM1. Okay. Okay, so in this case, if you are observing, your heat is added reversibly at the constant pressure. So in that case, that temperature will be the infinite temperature. So if the we are adding the uh, uh, heat at the mean temperature, so in that case, your efficiency um, will be higher in this case. That means higher the mean temperature of heat addition, the higher will be the cycle efficiency. Okay. So let me draw the diagram properly. Okay, so we this is the diagram for the Rankine cycle where we have shown the mean temperature. So this is the mean temperature line. So we have drawn the diagram in such a way that the area under this 4s and 1 is equal to the area under the 5 is 5 and 6. Okay, so in this case the area we have taken the same so that the heat addition will be same in both the case, right? So in this case we have to find out that your Rankine cycle efficiency is the function of the temperature only. So that we are going to find out. So if there is the in this case, the heat addition is how much? That is the heat addition is at 1 to 4s, right? So the heat addition is at the constant pressure. Let us find out what is the heat addition. In this case, the area we have taken the same. So in this case, the heat addition will be the Q1 is equal to your H1 minus H 4s, right? So this one we can also write down in terms of your mean temperature, that is your Tm1. So similarly we are also doing the surrounding temperature को लेके हम लोग क्या find out करते थे, हम लोग useful जो work find out कर रहे थे, available work if you have remember, that is the T0 delta S. Hmm, right? So there I have explained you this. So this equation we have to use in this case. What is the Q1 in this case? So Q1 in this case we are representing in terms of your mean temperature, right? So mean temperature that is your Tm1. So heat addition I can write down as Tm1 into your S1 minus S4s, right? So this is the useful work we can say. So because area under this 1 and 4s is similar to the area under this 5 and 6, right? So the heat addition I can represent in terms of the mean temperature also. So from this equation, that the mean temperature we can write down as Tm1 is equal to your H1 minus H4s upon your S1 minus S4, right? So this is your mean temperature we can find out from this relation. So similarly, what is the heat rejection? So heat rejection is done at the constant pressure, that is the process 2s to 3, right? So it is your heat rejection. So heat rejection, I can write down that equation. That is your H2S minus H3, right? H2S minus H3. So this one in terms of the entropy and temperature, I can write down as it is the in this case the temperature is let us take that is the T2 temperature, right? So ये है आपका T2 temperature. Hmm. So T2 temperature is multiplied with S1. So here entropy is same. So आपका S2S जो है ये आपका सेम रहेगा S1 से. So this will be the S1 minus. So it will be the S3. So I can write down it is the entropy is same. That is your S3 is S4S, S1 is S2S, right? So in place of the S3, I can write down as S4S, right? So this is your heat rejection. So now I can write down what is the Rankine cycle efficiency. So Rankine cycle efficiency is your eta, which is equal to 1 minus Q2 upon your Q1. So this equation always we are using in case of the heat engine. So which is equal to 1 minus, in place of the Q2, I can write down as T2 S1 minus S4S, right? So this is Q1. So Q1 I can write down it is the Tm1 S1 minus S4S, right? So this equation both will be get cancelled. S1 S4 S these two will get cancelled, and the equation will reduce to eta r is equal to 1 minus T2 upon Tm1. So if you are observing in this case, your efficiency of your Rankine cycle will depend upon the T2 temperature. T2 temperature means the temperature at which heat is rejected, and your mean temperature. Okay. So if you are observing in this case, if this T2 temperature is lower at a given value of your mean temperature, then we are getting the higher efficiency of the Rankine cycle. So this value can be lower up to the surrounding temperature. So we cannot lower than that one. That is your surrounding temperature is your T0. So that is your lowest practicable temperature of your heat rejection, uh, where your mean temperature is fixed. In that case, we can get the Rankine cycle efficiency is your maximum. So from this relation, we can infer that your Rankine cycle efficiency is your function of Tm1 only, because we can reduce this T2 temperature up to the surrounding temperature. So higher the mean temperature of heat addition will be the higher of the Rankine cycle efficiency. Okay, so uh, this is the mean temperature relation. So that mean temperature, if you are comparing with the maximum temperature of your steam that can be used in case of the turbine, that is that maximum temperature is temperature of the steam is fixed due to the metallurgical consideration. So I can write that the maximum temperature of the steam uh, used in Rankine cycle or steam power plant is restricted for metallurgical consideration, or we can say so we can say that materials used for manufacturing of components. Okay. So, in case of your Rankine cycle, that maximum temperature, we can go up to the metallurgical consideration of the component. So, whatever the material is used to make the components, so that is restricted up to the use of the high temperature steam and high pressure. So there are the different components like your superheaters are used, valves are used, pipelines are used, inlet stages of turbines. That means inlet stage of turbines में हम क्या use करते हैं? Nozzle, we are using the nozzle, right? So in that case, so that all those things will depend upon the maximum temperature of the steam. So that maximum temperature of the steam, um, that is also related to your mean temperature, that is your Tm. Uh, T max and Tm both are related to each other. So suppose there is the maximum temperature, this maximum temperature is fixed. Okay, so this value is fixed. Then your operating pressure at which your mm, mm, operating pressure of the boiler. Let me draw that diagram. So if you are observing in this case, this is your TS plot. In this case, we have taken the maximum temperature of the steam. So if it is the fixed one, T max is fixed in that case, your operating steam pressure at which your heat is added, that will be increased from the P1 to P2. Okay, to get this maximum temperature. Okay, so in that case, your mean temperature of heat addition also increased. So that means in this case, as we can observe that P1 to P1 pressure is increased to the P2 pressure. In this case, your heat addition, mean temperature of your heat addition will also increase. So if you are observing in this case, this is the mean temperature, that is 7 is mean temperature of heat addition. So here in this case, 1 to 4 is, this is um, mean temperature of heat addition. So if you are observing in both the case, if T max is fixed to get the maximum work, your P1 pressure will increase to the P2 pressure. Also, your mean temperature of your heat addition will increase. The heat addition will increase in this case. So your mean temperature will be more in case of the 7S and 5. Okay. So if you are observing in this case, suppose your P1 pressure is increasing to the P2 pressure. So turbine inlet pressure will also increase in this case. So this is the turbine stage. So here the pressure will increase to the P2 pressure. So ideal expansion process in this case, if you are observing, that will slightly shift to the left hand side. So initially, if you are having the P1 pressure, so in that case, your expansion will done up to this position. If your pressure is increasing, if your maximum temperature is fixed and you are you want to increase the work output, in that case we are increasing the pressure. So inlet pressure of the turbine will increase. So in this case, the expansion will be shift to the slightly left hand side. So what is the meaning of it in this case? The uh, quality of the steam at the turbine outlet will be decreased. So in this case, we are getting the more moisture content, right? So turbine exhaust will have the more moisture content. So if you are taking the quality of steam, that is the XCS, in this case X2S. So the moisture content will be more in case of the high inlet pressure of the turbine. So that is the CX, XCS is greater than X2S. Okay. Suppose the moisture content is more at the largest stage of later stage of the turbine, so it may corrode the turbine blade, or there will be the some erosion will happen in case of the turbine blade. So in that case, so we have to restrict that moisture content uh, of the expansion process. Okay, right? Got my point? So that's why, so there is some limitation of the mean temperature of heat addition is also restricted. So mm, um, for consideration of your erosion of the turbine blades, so larger stages of turbine are mostly considered. So in that case, the machine in that case, your maximum moisture content should not exceed than the 15%. So it is the uh, maximum 15%, or we can say that the quality um, should not be less than 85%. Okay. So in it is the desirable limit for the most of the turbine expansion process. So that expansion process should be take place in the single phase or vapor region only. So there should not be much moisture content in case of the turbine. So यहाँ पे देखिए कम है, यहाँ पे बहुत ज़्यादा है. So latest stage of the turbine expansion process में क्या होगी? You will have the more moisture content. Okay. So the maximum turbine inlet temperature or minimum heat rejection of the minimum temperature of heat rejection. So that are limited as per the materials used in case of the steam power plant. Okay. So these are the things we have to consider. So there should be certain maximum operating pressure related to this maximum temperature, so that we can have the less amount of moisture content at the turbine exhaust. Okay. So these are the relation of your mean temperature of the heat addition at the one temperature, minimum temperature, we can add the uh, heat, or minimum pressure we can add the heat. Okay, so next one is after the reheat minimum temperature discussion, we can discuss the what is the reheat cycle. So reheat cycle already I have told you, so you may have remember all these things. So reheat cycle means in that case we are increasing the work output of the steam power plant. Output of steam power plant. So here what we are doing, we are performing the expansion of the steam in two stages. One is um, in case of the high pressure turbine. So in later stage we are performing the low pressure turbine. So here we are using the HP turbine and LP turbine, right? So I think you have remembered these things. So in case of the discussion here in this case, so we are limiting the your maximum pressure of the steam. So in order to limit the quality of your steam, so in this case, what we are doing to increase the Rankine cycle efficiency. So there, your P1 max is fixed. Okay, so that achieve we can achieve quality of steam is up to 0.85. Okay, so x is equal to 0.85. So that in that case we what we are doing, we are performing the um, expansion of the steam in two stage. So initially what we are doing, so let me draw the diagram first. So reheat cycle ka diagram. So after the boiler, there will be the inlet to the turbine. Okay. So first is the high pressure turbine expansion over here. So this is the inlet, that is we can write as one, right? So this is the high pressure turbine. So then again the outlet of the steam, it will be again reheat. So that outlet pressure is, let us take that is the P3 pressure, right? So then again what we are doing, again that pressure, high pressure and high temperature steam will be the inlet to the low pressure turbine. So that low pressure turbine will be driven by the high pressure turbine. Okay, so एक ही साथ में connected है. तो ये है आपका low pressure turbine. So this will be the inlet to the low pressure turbine. So here what we are doing, we are adding the heat. Okay, so the ATP P3 pressure. So this will be inlet. So let us take this is the 2S, 2S, and this one is the inlet is your T. Okay. So then again the expanded steam will expand in the low pressure turbine. So here we will get the work output, that is the turbine work output WT. So this is the shaft. It is connected to the generator so that we can generate the electricity. So then turbine outlet, that is the after the expansion of the steam. So let us take that stage is your 4S. Okay. So here the pressure is your P2. Okay. So that is entering to the condenser. So this one is the condenser. So here it is the there will be the heat exchange of the steam with the liquid. So that is the water itself only. So this is the circulation water. Okay, so this is the outlet and this is the inlet. So here we are having the Q2 heat rejection. Then there will be the condensate will form and that will out from the condenser at the point. Let us take that is the 5. This is the point 5. Then there will be the compression process after the formation of the condensate. So that condensate will be compressed with the help of the pump to the pressure P1. So here it is the P2, here it is the P1. So that condensate will enter to the boiler at the point. Let us take that point is your 6S. Okay. So this one is your pump P. Here we are giving the work input, that is the WP work. Okay. So this is the schematic diagram or ray diagram for all the process in individual components. So this one is your this diagram is done for your reheat cycle. So here as I have used the two turbine to increase the work output, specific work output of the engine so that of the steam power plant so that it will not affect the quality of the steam. That quality of the steam will lies above this value. And here also we can use the maximum pressure so that maximum pressure so that their heat addition will be maximum. Okay, so that we can get the maximum efficiency of the cycle. Okay, so in this case, the optimum reheat pressure for the most of the modern device of the initial steam pressure. Steam pressure. Okay. So in case of the mm, reheat cycle, the mean temperature of retardation will depend upon the pressure. Okay. So to increase the maximum work output of the steam power plant, we can go up to the number of reheat process. So at the different constant pressure, the heating is done at the different constant pressure. You can go to up to the two reheat process and three, four like that. Okay. So in this case, let me draw the TS diagram. 1, 2s, 1, 2s, यहाँ पे P3 pressure melting 3, 4. So this is your again inlet is 3, then there will be the 7. I think it is visible to you all. I'm not going to correct this one. It will be difficult to draw this diagram in this digital pad. Okay, so this is the point. This one is the 4S. Okay, this is a point 4S. Five, six, five, six. So this is your TS plot, and if you are drawing the HS plot, it will look like this. P1, P3, P2, we will take a 1, 3, 2S, this is the 4S, 5, 6S. So this is your TS plot and this one is your HS plot. So molecular diagram or an enthalpy entropy diagram. So if you are observing this case, so the heat is added again in case of the uh, boiler, so that heat addition is done at the P3 pressure. So here the first expansion will done in case of the high pressure turbine, that is the S2S. So here the outlet of the turbine is the saturated vapor condition. Then again we are adding the heat to achieve the superheated steam at that maximum temperature. That temperature we are taking, that is your T max, and which is equal to T1 is equal to T3. So here again we are adding the heat so that we will get the quality of the steam which is greater than the 0.85. Okay, so if you are observing in this case, so this amount of work is increased by adding the heat in case of the reheat cycle. Okay, so this is the increase of the work. So in this case, this is the specific work output increase for the power plant. So in this case, due to addition of the heat in case of the reheat cycle, so here the steam rate will decrease. So overall cycle efficiency will increase. Okay, steam rate will decrease and specific power output will increase. Will increase. Okay, so that overall output of the plant will increase. So in this case of the heat addition, we can take the both the case. One is the 6s to 1, another one is a 2s and 3 process. So heat rejection will be that is a 4s to 5. So what will be the cycle efficiency? We will get that. Let me write down what is the heat addition. Q1 is your heat addition. So heat added at this process as well as at this process. So Q1 is equal to your H1 minus 6S HCX H6S plus your here again we are adding a heat that is the H3 minus H2S, right? So similarly your heat rejection will be here in this case that is your H4S minus H5. Similarly, your turbine work will be in case of the two stage. So first stage is your H1 minus H2S plus H3 minus H4S, right? This is your turbine work output. So similarly, we can find out for the pump work output that is your H6S minus H5. Okay, so now your efficiency of the Rankine cycle will be, reheat cycle will be, how much that is your WT minus WP upon your heat input that is your Q1. So in place of the turbine work, it will be H1 minus H2S plus H3 minus H4S minus H6S minus H5. Okay, so heat input we can write down this one. So in this case, high pressure are used in case of the reheat cycle. So in this case, the pump work is will be the appreciable one. Um, so in this case, your specific work output will be increased. So suppose your runtime cycle is operating with a single turbine, and there we are having the adjust of the steam is at this condition. So this will be the quality of the steam that is the X4 dash S. If you are reheating the steam again to get the superheated steam, in this case your work output will increase and the quality of the steam will also increase. So in this case, the steam power plant will operate with the high pressure. So increasing of the number of reheat cycle um, will increase the high pressure steam in case of the turbine inlet. But in that case, if we are going and increasing the number of reheat process, so in that case, what will happen? Mechanical stresses will develop. So with the increase of the pressure, so which will also increase the temperature of the plant, so that it should not be increased up to the certain limit. So number of reheat should be fixed as per the design of the steam that whole system. Okay. So this is all about your reheat cycle. So you can solve some problem related to this one. Okay. So let me take your attendance. If you have any doubt, please ask me. So rule number one,
Present, ma'am.
two,
Present, ma'am.
three,
Present, ma'am.
4,
Present,
4,
ma'am.
5,
Present,
Present,
ma'am.
ma'am.
6,
Present,
Ma'am.
ma'am.
7,
Present.
8,
Present, ma'am.
9,
Present, ma'am.
10,
Present, ma'am.
11, 12,
Present, ma'am.
13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Present, ma'am.
17,
Present, ma'am.
17,
Present, ma'am.
18,
Present, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Present, ma'am.
24,
Present, ma'am.
25,
Present,
26,
ma'am. 25
26,
present, ma'am.
26, 27,
Present, ma'am.
28, 29,
Present, ma'am.
30,
Present, ma'am.
31,
Present, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34,
Present, ma'am.
35,
Present, ma'am.
36,
Present, ma'am.
37,
Present, ma'am.
38,
Present, ma'am.
39, 39, 40, 41,
Present, ma'am.
42,
41
Present, ma'am.
43,
Present, ma'am.
44, 45,
present, ma'am.
48,
Present, ma'am.
49, 50, 51,
Present, ma'am.
53, 54,
Present, ma'am.
55,
Present, ma'am.
56,
Present, ma'am.
57, 58, sorry, 58 is absent, 59,
Present, ma'am.
60,
Present, ma'am.
61, 61, 62,
Present, ma'am.
63,
Present, ma'am.
65,
Present, ma'am.
66,
Present, ma'am.
67, 68,
Present, ma'am.
69,
16 present, ma'am.
70,
70 present, ma'am.
71, 71, 72,
Present, ma'am.
73,
Yes, ma'am.
74,
Present, ma'am.
75,
Present, ma'am.
76,
Present, ma'am.
77,
Present, ma'am.
78, 78, 79, 80,
Present, ma'am.
81, 82,
Present, ma'am.
83, 84,
Present, ma'am.
85, 86,
Present, ma'am.
87, 88,
Present, ma'am.
89,
Yes, ma'am.
90,
Yes, ma'am.
91,
Present, ma'am.
92,
Present, ma'am.
93,
Present, ma'am.
94,
Yes, ma'am.
95, 96, 97, 98,
Present, ma'am.
99, 100,
Present, ma'am.
101,
Present, ma'am.
102, 102, 103, 104,
Yes, ma'am. 104.
Ma'am, 102
105,
present, ma'am.
105 present, ma'am.
105,
Present.
106,
Ma'am,
105.
102 present.
106, 107,
Present, ma'am.
108, 109,
Present, ma'am.
110, 110, 111,
Yes, ma'am.
112,
Present, ma'am.
113,
Present, ma'am.
114,
Present, ma'am.
115,
Present, ma'am.
116,
Present, ma'am.
117,
Present, ma'am.
118,
Present, ma'am.
119, 119, 120,
Present, ma'am.
121,
Present, ma'am.
122.
Present, ma'am.
Okay.
चैट बॉक्स में
मैम
मैं बहुत
71 प्रेजेंट
लिखा।
है मैम।
चैट बॉक्स में आप लोग क्यों इतना लेट में करते हो बताओ?
मैम
माइक
71 मैम
लेकर।
प्रेजेंट कर दीजिए।
हाँ ओके
Ma'am,
ओके
102.
ओके। नहीं और नहीं, क्या करे थे तुम लोग? 102 प्रेजेंट है। ओके थैंक यू ऑल।
Ma'am, 53.
मैम हैंड आउट भेज दीजिएगा और
हाँ
पीपीटी।
हाँ ओके, उसको मैं भूल ही जा रही हूँ, भेज दूंगी। ठीक है ओके बाय।
मैम मैम 71 प्रेजेंट है मैम।
नहीं एब्सेंट है।
मैम प्रेजेंट है मैम।
ओके
चैट बॉक्स में लिख दिए थे, माइक पर क्यों कर रहे थे?
गुड।